So good day everyone. This is the second topic that we will discuss for ES17 or Engineering Mechanics 2, which we will tackle about rectilinear kinematics for erratic motion. So last time, what we had discussed is about the continuous motion, and what you have learned was the different kinematic equations that you can use on solving rectilinear kinematics. So talking of erratic, when we define actually erratic, that is defined as changeable. And when we differentiate erratic to continuous motion, so when a particle has erratic or changing motion, then its position, velocity, and acceleration cannot be described by a single continuous mathematical function along the entire path. So what we had discussed on the continuous motion, it is actually described only by a single continuous mathematical function. But if you encounter a particle that is described by more than two mathematical functions along the entire path, therefore, that motion is what we call an erratic or changing motion. So instead, a series of functions will be required to specify the motion at different intervals. So how can we actually solve a motion that is erratic or changing? So for this reason, it is convenient to represent the motion as a graph. So if a graph of the motion that relates any two of the variables s, v, a, and t can be drawn, then this graph can be used to construct subsequent graphs relating two other variables, since the variables are related by the differential relationships, which are the three kinematic equations. Okay, so let us discuss the different types of graphs that you may encounter in this topic. So the first one are the ST, VT, and AT graphs. So in a given problem, it depends if what graph is given. If ever ST graph is known or given, you will construct first the VT graph using the V is equal to ds over dt of the kinematic equation, since it relates the variables s and t to the variable v. So this equation states that the ds over dt is equal to v, which is defined as the slope of st graph, which is equal to the velocity. So if this is your st graph, you can construct your corresponding vt graph, and the slope of your st graph are the points for your vt graph. The next one, once you construct the vt graph, you can construct also the AT graph in a similar manner using the kinematic equation A is equal to dv over dt. So the dv over dt is the slope of the vt graph, which is equal to the acceleration. So if this is your VT graph, you will construct the corresponding AT graph. So the slopes at each point sa imuhang VT graph will be the points for your AT graph. And for the ST, VT, and AT graph, what you will apply is actually derivative, which will be discussed later on. If ever, instead of ST graph is given in a problem, if ever AT graph is given first, you can construct the VT graph using, again, this kinematic equation, which is A is equal to dv over dt, and it is written as delta V is equal to integral of a dt. So that is the change in velocity, which is equal to the area under the AT graph. So hence, to construct the VT graph, it begins with the particle's initial velocity, that is VO, and add algebraically to this small area increments delta V to that is determined from the AT graph. So if this is your AT graph and the small area increments here that is represented as the delta V are your points to consider to form the VT graph. And take note, areas lying above the t-axis correspond to an increase in V, that is the positive area. So as you can show, as shown here in this figure, since the areas here in the AT graph is above the t-axis, so when you construct the VT graph, it will have an increase in velocity, therefore it is a positive area, whereas those lying below the axis indicate a decrease in V or a negative area. Once you construct the VT graph, in a similar manner, you can construct the ST graph using this kinematic equation, that is V is equal to ds over dt, and it is written as delta S, which is the displacement, which is equal to the integral of V dt, which is the area under the VT graph. So if this is your VT graph, you can construct the ST graph from the VT graph using this kinematic equation. Hence, to construct the ST graph, it begins with the particle's initial position SO and add algebraically to the small area increments delta S determined from the VT graph. So when you construct the other graphs, it depends of the known graph in the problem. If the known graph in a problem is an ST graph, so the first graph you will construct is the VT graph using the kinematic equation V is equal to ds over dt. Then afterwards, you will construct the AT graph from the VT graph using the kinematic equation A is equal to dV over dt. In a similar manner, if ever a problem, if the known graph is an AT graph, so the first graph you will construct or you will draw is the VT graph, and you will construct that using the kinematic equation A is equal to dV over dt. Then afterwards, you can construct already the ST graph from the VT graph using the kinematic equation V is equal to ds over dt. So on the first one, it is by using the derivative, and on the latter latter example, or if ever the AT is known and then VT then ST, what you will apply is by integration. So these are the other types of graphs. These are VS and AS graphs. So here is if ever VS graph is known or given in a problem, so you will construct the AS graph using the this kinematic equation, the third kinematic equation, ADS is equal to VdV. So it is written as A is equal to V times dV over ds, which is the acceleration equal to the velocity times slope of your VS graph. So if this is your VS graph, you can construct the corresponding AS graph, and at any point in your VS graph, the slope dV over ds of the VS graph is measured. Then with V and dV over ds known, the value of your acceleration can be calculated. On the other hand, if AS graph is known or given in a problem, you can construct the VS graph using the same kinematic equation and integrating this equation between the limits. Therefore, you can come up with this equation. And if you have this AS graph, you can construct the corresponding VS graph. And if the red area in the figure is known, then uh, uh, if the red area in the figure is determined rather, and the initial velocity at the initial position is known, then you have this equation, and successive points on the VS graph can be constructed in this manner. So the same thing, if ever VS is given, you can construct the AS graph using the kinematic equation ADS is equal to VdV, and what you will apply is using the derivative. And on the other hand, if AS graph is given, you can construct the VS graph using the same kinematic equation but by applying integration. So that is the difference between the graphs that was discussed earlier. So later, I will discuss some example problems. We will solve 3 example problems about erratic motion. And since we are talking about graphs, you can use actually other or online graphing calculator or app in your mobile phone or tablet, which you can draw your functions. So I will show you later during whenever I discuss um, the example problems. And also take note, on the previous graphs, if I go back on the ST, VT, and AT graphs, horizontal axis represents the time, and the vertical axis represents the position S, velocity V, and the acceleration A. For the VS and AS graphs, that is the horizontal axis is the position S, and the vertical axis is the velocity V and the acceleration A. Now let us proceed on solving the example problem.